Okay, so I think it's time to start. I'm Daniel Warshofsky. I'm here at the University of Minnesota working with Michael on SCOPE, which is the uh, ZTF variable classification project. Um, and it's a supervised learning technique, which you guys learned about earlier. So I'm going to kind of dip into a little bit of a little outside of my wheelhouse here to teach you about unsupervised learning. Uh, so yeah, the presentation is more supposed to be kind of an overview of a couple of unsupervised learning kind of in general, and then a little more in depth on three specific algorithms, where I'll sort of explain how the algorithm works. And then the main focus is going to be on the notebook where you're going to be using the sklearn implementations of these three algorithms on a data set from BTS. So that's kind of the rough outline of this presentation. Okay, so unsupervised learning in general, the big difference between supervised and unsupervised learning is unsupervised learning does not have user-defined labels. So in a classic supervised learning problem, you might have pictures of cats and dogs, and you tell the machine what's a cat and what's a dog. In contrast, in an unsupervised learning situation, you may have pictures of cats and dogs, but you don't tell your algorithm what's a cat and what's a dog. It's sort of up to whatever algorithm you choose to decide how to group things. So sort of an advantage of unsupervised learning is that like this not having to pick labels. I don't know if you all have had to manually label data, but that can be very tedious, especially if you want a robust training set for supervised learning. So, that's sort of an advantage. Another thing is depending on what algorithm you use, the the number of clusters or labels can either be user defined or chosen for you. So, for example, if you had cats and dogs and you somehow knew there were two different animals in your pictures, you could tell an algorithm that there are two different clusters and it'll try and figure that out. Or some will figure it out on their own. So yeah. These techniques are typically used for clustering, so kind of grouping like data together. But sort of the main disadvantage is that the interpretations of classifications can be dubious. So what I may decide is relevant for clustering is not what an algorithm will decide is relevant for clustering and may be sort of unphysical. So in this cat and dog example, if the background of half the images was a beach and half of it was a forest, but you wanted to group cats and dogs, the algorithm may decide to group things by what the background looks like. So it's sometimes it can be unclear how this grouping is done, um, which is uh, kind of my motivation for explaining how some of these algorithms work, so you can understand the steps that go into defining these different clusters. Um, yeah. But if you stick with physical clustering problems, like for example, figuring out what stars belong to a cluster, the interpretation um, is more physical and easier. So, a cluster is actually a cluster, not some kind of esoteric grouping. So now I'm just going to go, or if there are any questions, if there aren't any questions, I'm going to go on to uh, a couple of example algorithms. So example algorithms. Kind of the first and most simple algorithm is k-means. And so here I kind of just have in words what happens. So first you partition your data into you pick a random partition of your data into n n how do I write here? Yeah, n data points into j different clusters. So in this algorithm, you pick the amount of clusters. So you so you pick J clusters, you divide all of your points. You pick a partition, which is a disjoint grouping, and then you compute the mean of these clusters. And then for each point, you want to minimize the inertia, which is this equation here. Basically, what you're doing is you're finding the closest mean to the data point and keeping that value and add it to a running sum. And this is the quantity that you want to try and minimize. And then at the end, the labels are what if the point, whatever partition the point falls into. So, okay. So now I'm going to kind of schematically go through the steps of the algorithm. So here we just have some random data scattered around in our sort of data plane here. The first step is to pick a partition. So let's just randomly pick up a partition here, represented by the colors. I'm sorry for the red-green colorblind people. I just realized. Okay, so we pick a random partition, then we compute the means, which are these x's here, and just so you can see the means clearer, I'll just take the points away. And then for each of these points, we're going to go through and compute the inertia. So we take this point and we compute the distances to these means here, and we take just the minimum one and add it to our sum. So here. Right, so this is the closest one, but if we look back at our original data, this is a red point, not a green point. So this is not, this is not an ideal grouping because we would want, the red point should be close to the red mean. So now we reassign the points to their closest mean, which is done here. So now we have a new partition, and then we recompute the means. So we just go through this iteratively until we reach some threshold where our inertia doesn't change enough, or we reach some value we're satisfied with. Does that make sense on how this is computing? Okay. So now I want to ask you guys a question. So what might be some disadvantages of using an algorithm like this to do clustering?
You're certainly throwing away information.
So
You're throwing away information.
what kind of information are you throwing away?
Well, I mean, some points end up becoming other points because you don't account for scattered. I mean, it's gonna have the same mean if it's in the middle of a circle display or a circle display.
Right.
It's overlap. You're throwing away the overlap information.
Right.
Spatial, I mean, in this case, like spatial overlap.
So that's part of it. What about any other?
Get the initial guess.
Random. We just pick a random partition.
In that case, we're very sensitive to that initial condition.
Correct. So yeah. So you can be sensitive to the initial condition, and it kind of determines how these means will move around. Right. So every point is going to be part of a cluster. Yep. Right. That's another thing. Yeah. That's sort of a user-defined parameter, the number of clusters. So it's unclear, like in this scenario, I may, realistically, this may be just one cluster. There may not be two separate things going on here. So, okay. Any other ones?
Hi, am I audible?
Plane of data we're looking at is the relevant one.
Right. That's that's kind of a generic problem in machine learning of picking what features are good. So let me get to my slide here. So yeah, here's just a couple of disadvantages that I labeled off. So computation time, this can be expensive. So each iteration we need to compute j distances for endpoints. So this this can scale poorly. As well, in higher dimensions, distances kind of are inflated, so that also leads to issues. And kind of a big one here that you guys didn't really mention is the shape of the clusters is fully determined by the distance metric you use. So in this case, I use just the standard Euclidean metric, which gives you spheres. So any kind of data or cluster that isn't a sphere is not going to be able to be captured by this kind of method. So I think I said like so any convex cluster. So like a crescent shaped cluster isn't going to work here because k-means with this Euclidean metric is only going to give you, vaguely spherical clusters. So that's kind of a big disadvantage. One that I didn't put here, which is a good question to think about, is determining the number of clusters. That's kind of vague, and k-means isn't quite equipped well to help you determine the number of clusters. Okay, so any more questions about k-means before I move on to the next one? Okay, so the next one is DB scan. So it's density-based spatial clustering of applications with noise. So here there are two tunable parameters, which are epsilon, which is a small distance, and minimum number of samples, which is an integer. And importantly, the number of clusters is not a tunable parameter for this. So unlike k-means, the number of clusters is going to be fully determined by dbScan. And the way that this algorithm works is it assigns points to be cores. So a core point is defined as a point where there are at least minimum samples within epsilon distance of it. And the cores and their neighbors together form a cluster, and anything that is not a neighbor of a core is left out. So that would be like outliers, or so sort of like outliers. So now I'm going to kind of schematically show you how this algorithm works. So again, here we have some weird shape of data. And for this example, I'm going to pick minimum samples 3. And then this circle represents the size of epsilon. So these are the two things you're changing. This number here, the amount that you pick, and the size of this circle. So first we start off, we pick a random point here, and we look and we see there's 1, 2, 3, 4, 5. There's more than 3. Let's see how many I picked here. Yeah, so there's more than 3 within epsilon. So this gets labeled as a core point. And then all of these ones are its neighbors. So now we move on. We pick, so more than 3 points, so it's a core point. So now we pick a new point here, and we see that this is a neighbor of this core point, and it also has at least 3 within epsilon. So it becomes a core point as well. So we just keep doing that on and on and on until we reach the end. So here, all of these points had enough nearby, so they became core points. But these points here aren't core points, but they're neighbors of these blue core points. So if you notice here, the density has dropped compared to here. So there aren't enough points in this region to kind of bridge the gap here. So then we pick another point, and this has enough points with an epsilon to be a core point, and so on. And I've labeled the points there. And then we have this green point here at the top where it doesn't have the minimum number of samples within epsilon, but also it's not a neighbor of one of these core points, which are the darker ones. So it remains unlabeled, kind of in these outliers or orphans. And then so we fill the rest in, and we have this grouping. So dbScan on its own decided that there's two main clusters as well as these outlying ones. Does that make sense how dbScan is working through here? Yeah. Okay. So I'll kind of ask the same question. What are some disadvantages that may come from this kind of method?
You're biased by how first cluster works. I mean, you're biased from where you start.
Mm-hmm.
Maybe not in this example particular, or it's not very striking. But for example, there's like that point of light blue one in between the blue cluster and the red one.
Yeah.
That one. I mean, you could assign that to any of them, but start with the blue one, so you end up assigning it to the blue cluster.
Right. Right. So yeah, there can be some variation on the edges.
But
Yeah.
maybe, okay, I'm assuming that there might be something more significant depending on how you're thinking.
Yeah, so it can be I think it depends on the implementation. So some easy way you could do a tiebreaker is, pick the closest neighbor and then you choose that one to assign. But yeah, so that's one issue. Any other considerations?
That's just like the very first guess. I mean, we have not varied our parameters. But
Right, so that's another thing.
very ambiguous.
Yeah, so the parameters are kind of ambiguous of how you might choose them. So picking the number of clusters, that's a very intuitive parameter to tune. It's asking the question how many groups there are, but asking the question how many points should be close enough within what distance is kind of difficult to interpret. So that's kind of a big disadvantage of this. And yeah, anybody else have one before I reveal my answers? Yeah.
The single point also be considered as one cluster because we gave the minimum number of clusters we wanted to be three.
Mm-hmm.
Maybe there are two main clusters over here and then.
Yeah. Yeah. So typically, how this algorithm works is there's always at least two clusters where there's, a cluster that has these core points, and then all of the points that don't belong are sort of grouped together. But you're never going to have a point alone be its own cluster because if there's nothing neighboring it, you can't have 0 as your minimum sample. So a cluster is always going to have at least 2 points in it. So you're never going to get, just a bunch of random clusters. Part of the notebook is going to be playing around with the parameters and seeing what you can get out of them. Okay, so yeah, so some disadvantages. So some of the ones we said here, yeah, so the parameters are unintuitive. That's sort of a big one. It's very difficult to justify what you pick. And since you don't know in these scenarios, you don't know what the real answer is, so it's very difficult to kind of base it off of anything. So yeah. One is, so you're only considering local information. So at each point in the evaluation of the algorithm, you're only looking at most epsilon away from any single point. So if there are any sort of long range correlations, dbScan is not going to see that unless there's a set of linking points between them. Yeah. Also, all the classes need to have the same density. So if you have one cluster that's very dense and one that's kind of sparse, normal dbScan is not going to be able to handle that because the sparse one is not going to be able to generate as many core points. And that's something you'll see in the notebook, where one cluster is more sparse than the other, and you'll see that dbScan has a difficult time handling that. There is HDBScan, which I haven't experimented with myself, that can sort of dynamically vary the epsilon value to try and help with that. But yeah, normal dbScan has a huge issue here. But one thing to point out, compared to k-means, we have a very non-spherical cluster here. So k-means would have, picked a circle here and a circle here, but dbScan is able to kind of get some of this convex shape. So that's kind of an advantage here. Okay, and then any last questions on dbScan? Okay, so the last one that I'm going to go over before we go to the notebook is Gaussian mixture model. I don't have a little schematic for this one because I think this is pretty intuitive. Basically, you're asking the question, or you're asserting that the data is coming from a mixture of finitely many Gaussians, and you're just doing you're just fitting, say, like 5 Gaussians to your data. What's nice about this method is that in principle you can incorporate error, which k-means is really not able to do, as well as dbScan.
Because my supervisor was
And,
using
the
usually
statistical
mixture
foundation
model.
is nice because you can
It might be more
use a lot of
difficult than-
tools like the Bayesian information criteria to help you determine the number of clusters. So that's something that's in the notebook. And kind of a disadvantage similar to k-means, you're enforcing the shape of your clusters. So here the clusters are assumed to be Gaussian. So if you have non-Gaussian clusters, this is not going to find that. I don't have a schematic for this because it's this one. I feel like this one's a little more intuitive. You're just fitting multiple Gaussians, and it's learning the standard deviations and means of the clusters. That's what it's doing here. Okay. Any questions? Yeah. If there aren't any questions, I think we should go into the notebook. It's under lectures, it's 03-UL is the directory where the notebook is. And yeah, so basically in the notebook, you're going to look through a data set that I have selected to make this exercise work.